In this video, we're going to look at set operations. So what we're doing is we're looking at what happens when we have two sets, what we can do and what we can talk about with those two sets. The first thing is the union between two sets. So the union is the idea that we're bringing the two sets together. So we denote it with the union notation here, the A union B. And what that means is that X can be an element of A or X can be an element of B. So here, let me write that with the set builder notation. That's how that set would look. That is A union B. So it could be an element of either one of them. Basically, we're putting the two sets together. So for example, let's say these are our two sets, 1, 2, 3, and 3, 4, 5. If we're putting these two sets together, that union is going to look like 1, 2, 3, 4, 5. Notice I'm only writing the 3 once. It's not necessary to write it twice. And here, I do want to demonstrate the Venn diagram for these. So visually, what we're looking at is, if this is the set A, and this is the set B, the union is everything inside A and everything inside B. And then outside of that, that's the universe and whatever's left over. All right, not bad. Okay, let's look at intersection. So intersection, which we denote with the upside down U, that is elements that they have in common. So in other words, X will be an element of A and X will be an element of B. That's how we would write the set builder notation for that. So our last example is actually a good one. What would be the intersection of these two sets? Well, the thing they have in common, the thing that's in both sets is 3. So that would be the intersection. Visually, let me go ahead and do the Venn diagram. What's in common there with two sets is what is in their overlap, the part where the two sets cross over each other. So this part right here, that would be the intersection. What if they don't have anything in common? Like part B here, 1, 2, 3, and then 4, 5, 6, they have nothing in common. Well, in that case, it's the empty set. It's possible for them not to have anything in common. Okay, the complement, and this is with respect to the universe that we're looking in. The complement is everything that's not in A, everything that's not an element of A. So there's a couple ways to write the complement. One way typically is to say that it's just not in A. That's simple because then it's implying that it's anything's just not in A. They do sometimes, some books actually make a point of mentioning that it's in the universe, U, but it's also not in A. They could use the double bar notation or potentially the and notation. So both would have to be true, but really it is the simple statement that I wrote first. Okay. Mentioning just real quick that sometimes complements are denoted by A to the C. The book called that out. I've also seen it denoted with a prime notation. I've seen some books use prime. Primarily the books that use that are the ones that are like non-STEM, like for people who aren't really going to calculus, only because prime notation is something different in calculus. Okay, but our book uses the bar, so we will use the bar as well. If U is positive integers less than 100, what is the complement of this set? Well, that would be all X, where X is less than or equal to 70. So we're like switching the inequality, throwing the equal to sign because that is a possibility. Let me go ahead and draw the complement of this. So the complement of a set A is everything not in A. So I'm not even going to bother drawing another set because who cares? It's just outside of A. So if it's in A, it's not included. All right, there we go. Best I can do. My sad little highlighter. Okay, difference. Difference between sets denoted A minus B is the set of elements in A, but not in B. Okay. They also say it's the complement of B with respect to A, meaning anything that isn't in B, but is still contained in A. So what that means then, like, let's look at our example that we were looking at before. If A is 1, 2, 3, and B is 3, 4, 5, then A minus B is 1, 2, because those are things that are only in A, but not in B. So it's like complement, but they're in A only. Let me draw that as a Venn diagram. So we do have our two sets. Here's A, here's B. So A minus B is things that are only in A, oops, but not in B. Pretend it stayed inside the line, okay? There you go. Okay, so things only in A, but not in B. Real quick, I do want to make a note that we could go the reverse direction. Here, let me use a different pen. B minus A. So these are things that are in B, but not in A. So in this example, that would be 4 and 5, because those are things that are contained in B, but not in A. All right, real quick, just a little aside, the cardinality of a union. When you're looking at two sets and you're trying to figure out how many things are in the union, you could find how many things are in A, how many things are in B, but you do need to subtract then their intersection, because technically it's getting counted twice, right? If you're finding everything in A, that means, let me just kind of draw that out. If you're finding everything in A, here's A. There it is. Everything in A here. I'll use the yellow highlighter. There's everything in A. Okay. But then if we have a set B, and oops, it had selected the pen, but had not updated yet. Sorry. So here's everything in B. Let me grab a different color highlighter. Let's do pink. Okay. So everything in B is this. And what happens is that's what, if I find those two cardinalities, right? A is the yellow one, B is the pink one. What we have is this got counted twice. So we have to take it out once. So by subtracting out the cardinality of the intersection, how many things are in the intersection, since it got counted twice, that's how you find the cardinality of two sets. Okay. I did have to kind of leave a little space for the identities because I want to get them all on one page. These are from the book. Set identities. Some of them are really obvious, right? Like if you look at the union between A and the empty set. Sorry, let me grab my highlighter here. The A in the empty set, obviously it's just going to equal A. Or if you look at the intersection between them, it's going to be the empty set. Or if you union A with the universe, it's going to look like the universe, or the intersection is just going to look like A. All right. It's kind of boring. Most of these identities make a lot of sense. The complement of the complement equals A. They're commutative. What doesn't matter which way you write it. They're associative. They have distributive laws. We have De Morgan's laws, which we are going to prove here in a minute. And then what's called absorption laws and complement laws. So exciting. Okay, so let's look at a proof of De Morgan's law. So we're going to prove that if you look at the intersection between A and B and find their complement, that's the same thing as finding the complement of A and unioning it with B. All right, there's a couple ways to prove this. They are both shown in the book. The most elegant way of proving it is showing that what we look at is the set definitions, what's called the set builder notations for each of these that I've been kind of listing out. They end up kind of producing the other set builder notation. Okay, so let me kind of explain what I mean by that. If I'm saying that set builder notation for this, okay, the set builder notation for this is all X such that X is an element, I'm sorry, is not an element of A intersect B, right? That is the definition of complement. We defined that earlier. It just happens to be, we're looking at A intersect B as our set. Okay. Another way of writing this is to write the not, the negation statement. X is not an element of A intersect B. So that's by definition of negation. Allows us to do that. Okay, then I'm going to use the definition of intersection here to help me now. So intersection means that X is an element of A and B. But, oops, sorry. But technically there's still a not symbol out here. So that's definition of intersection. And then I can, this is where we're going to be kind of clever. Because of that not symbol out there, negation, I can actually use De Morgan's law from propositional logic that we learned in chapter 1. So De Morgan's law says that if I apply the negation symbol to each of these, that switches this to union. So that's De Morgan's law of propositional logic. And I'll just abbreviate propositional. So we saw that before. We talked about De Morgan's law for propositional logic before. Okay. I just realized I didn't want the union symbol. I wanted the and symbol. I'm sorry, which is then the or symbol. My apologies. I think I said or and didn't write it. I wrote the union. I apologize. I mean the U symbol. Okay. So now another way of saying that is to say that X is not an element of A, or X is not an element of B. That's a different way of saying that. And that's just using definition of complement again. Oops, I'm realizing, I think, yeah, okay, good. I spelled complement right the first time. The one with the I is when you say something nice to somebody else. Okay, but another way of saying that is that X is an element. Oh, wait, I'm so sorry. This is definition, not of complement. I'm about to use definition of complement. This is definition of negation again. Okay, now I'm going to use complement. Here we go. So that means that it's a member of A complement or a member of B complement. That's definition of complement. There we go. All right, we are so close now. So this, another way of saying this is saying that X is an element of their union, because that's definition of union. Which means we are just really looking at the union of these two sets. So what we started with was saying that if we're looking at a union B complement, that ends up being this, which is 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 this, and this happens to be the union of A complement and B complement. Yay, we did it. All right, so that's how you can show De Morgan's law. Another way of doing it, I do want to note really quick, is you could have shown that the intersection complement is a subset of this. And the reverse is true, that A complement union B is a subset of the intersections complement. So if you show both of those are true, and it's very similar argument, by the way, that also produces equality between the sets. So that's another way to do it, show that they're both subsets of each other. And in that case, you kind of drop the set builder notation and you just really are writing what's to the right over instead. All right, but you do have to write it twice because you have to go both ways. So it's a little bit tedious that way. Okay, so generalized unions and intersections. So we can say in general that we have a union of sets with no indicator of those sets themselves with this kind of generalized notation. If the sets happen to be A1 through AN, then we would be union A1, union A2, union ... up to A sub n. Now, technically, because I didn't indicate a stopping point, I could keep going ... forever for however many sets there are. But since there is a stopping point, it's wise to indicate that by saying I goes from 1 to n. So I'm going to do that down here. I is going to go from 1 to n. And therefore, I would be doing an intersection between all of these sets ... until I get down to A sub n. And there we go. Okay, I do have a problem for these because it is a little bit odd, the notation for this, and I want to kind of practice it. Let's say for I going from 1 to 2, all right, let A sub I equal this list I plus 1, I plus 2, I plus 3, I plus 4, ... Okay, it keeps going on forever. All right. So if I wanted to find the union for all of these sets where I goes from 1 to n, that's what they're asking me to find. I is going from 1 to n. That means I'm finding the union from 1 to n of this. Oh, sorry. I'll write that in a second. I, comma, I plus 1, comma, I plus 2, ... keeps going forever. So if I plug in my values for I, the very first one is just going to be the set 1. So here, let me list that out up top. A sub 1 is, thank you, A sub 1 is the set 1. The next number would be 2, 3, 4, and so forth. A sub 2 would start with 2, 3, 4, 5, and so forth. So the idea is it ends up listing the numbers. A sub 3 would start at the number 3, but the union of all of these is going to end up being the very first set. 1, 2, 3, so forth, or A sub 1. The union ends up being A sub 1 because A sub 1 contains all of the numbers that get listed out when we look at this set. Okay, so the intersection then, the intersection of these sets means we want to know what they have in common. Oops, sorry, I keep doing that. I plus 1, I plus 2. Okay, so in this case, where they start having things in common depends on where the last set is. So if the last set happened to be A sub 6, okay, here, sorry, let me do that in green. If A sub 6 happened to be the last set, if that was quote unquote n, that means it would start at 6, 7, 8, 9, ... and goes forever. Now, A sub 1 contains A sub 6, right? Because eventually I'm going to hit 6, 7, 8, 9 and keep going. Same with A sub 2. So A sub 6 would be the intersection for those 6 sets. If I were going to look at A sub 1 intersect A sub 2 intersect A sub 3 intersect, right? So A sub 1 intersect A sub 2 intersect A sub 3. Keep going until I hit A sub 6. They're going to equal A sub 6 because all of the previous sets contain A sub 6 in them. Therefore, this set is going to pick up on the last set, which is n. So n is the first number, and then it goes n plus 1, n plus 2, and dot, 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 it keeps going forever. Or in other words, it's the last set listed, which we're calling a sub n. And there you go.